All right, this is 33-4, and we're looking at the DI here. Now, when it comes to this, we're looking at verifying identities. Remember, we want to make one side look like the other, and it's helpful to make the more complicated side look like the other. So I'm going to even go over the intro example here as well. So on this one, probably this side is the more complicated. So this is actually distributing. This is cosine of theta minus sine theta times cosine of theta minus sine theta. So then multiplying all of that through, you're going to get cosine squared theta minus 2 sine theta cosine theta, and then plus sine squared theta, because that's going to be cosine theta minus sine cosine theta minus sine, and you're going through distributing it through. Now this cosine squared and this sine squared, if I add that together, I get 1, and then I have a minus 2 sine theta cosine theta is the sine of 2 theta, which is the same. Let's look at another one. Let's do number 2. So I have the tangent of 2 theta equals 1 over tangent minus tangent theta minus 1 over 1 plus tangent theta. So this side looks the more complicated, the right side. And so it looks like I need to find the common denominator. So this needs a 1 minus tangent theta over 1 minus tangent theta. And this needs a 1 plus tangent theta. So on the top here I get 1 plus tangent theta minus, now over here I get 1 minus tangent theta. This is all over 1 plus tangent theta times 1 minus tangent theta. Well, they're conjugates, so if I multiplied those together, the inner and the outer will cancel out. So I'm just left with 1 minus tangent squared theta. Now on the top here, if I distribute this negative, so 1 minus 1, that cancels out, and I have 2 tangent theta, which happens to be the identity of tangent 2 theta. I'll set up number 4. So we have 8 sine to the 4th power theta equals cosine of 4 theta minus 4 cosine of 2 theta plus 3. So it's probably easier to do the right side. That looks the most complicated. And I want to turn everything into sines. So that means at any possible interval, I want to try and get rid of cosines. So if I have a cosine of 4 theta or the cosine of 2 theta, I need to be thinking about, okay, what double angle identities do I know that will help me get rid of cosines? So in this instance, cosine of 4 theta, we know that that first identity is going to be, because I need to think of this as 2 times 2 theta. So that's cosine squared of 2 theta minus sine squared of 2 theta. And then I want to just completely get rid of that and turn it into a sine. So I get minus 4, and then cosine of 2 theta in terms of sine is 1 minus 2 sine squared theta. And then I have that plus 3. Now this right here, that cosine squared of 2 theta, that is also 1 minus 2 sine squared theta. And then this minus sine squared of 2 theta, that's going to be minus, let's see, how does that reduce? If we think of this as u, then we could say that that is, because this is going to be squared, 2 sine theta cosine theta. So all of that is squared. And then we still have that all broken down. So if you notice, all I'm doing is breaking all of this down. Now in this process, you will start seeing things cancel out, because the square is going to go to all these, and then we're going to be able to turn that cosine squared into a sine squared somehow using Pythagorean identities, and you're going to see things continue to break down. Number 5. I'm just going to set up the quadrant, and then you guys can perform the identities. So it says cosine of theta is 12 over 13, where theta is between 3 pi halves and 2 pi, so that's quadrant 4. Because this is 3 pi halves and this is 2 pi, so it's in between there. So adjacent over hypotenuse, which makes this 5, but it's going down, so it's a negative. So then my sine of theta is opposite over hypotenuse. My cosine theta is adjacent over hypotenuse, and my tangent theta equals opposite over adjacent. And then you can use the identities like the sine of 2 theta. It's 2 sine theta cosine theta. So that's going to equal 2 times sine theta times cosine theta. Dot, 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 dot. And then number 7. For this one, it actually doesn't really matter which one we use. Just looking at that, it's like, oh. I would say either side is equally difficult. I'm going to do the right. Why not? I like tangent. Tangent makes me feel more comfortable than secant. But noticing that, I noticed that secant squared and tangent squared probably have some sort of Pythagorean identities going on. But this tangent of the 4th power, so maybe if I factor out a tangent squared, then I'm going to be left with 1 plus tangent squared theta. Well, that right there is secant squared theta. This right here, if I look at the identity, I'm going to do that off to the side here. It's 1 plus tangent squared theta equals secant squared theta. If I subtract 1 on both sides, tangent squared theta equals secant squared theta minus 1. So then that is just going to be secant squared theta minus 1. Now multiplying everything through, you get secant to the 4th theta minus secant squared theta. Boom! We got it. Next one. It says find the slope-intercept version of the line parallel to the given line. So parallel means the same slope. So on number 8, just looking at that, m equals 1/2. And so y minus y1 equals my m times x minus x1. And then dot, 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 get y by itself.